Welcome everyone. I'm Eva Lee and will be your instructor to help you understand machine learning coding in Python. Today I will dive into machine learning with you guys, but don't worry, we will leave the heavy math textbooks at the door. Instead, we will just jump into the coding work. Why does machine learning get popular and important recently? Imagine that you could predict housing price, classify disease from medical data, or detect spam emails, all with just few lines of Python code. That's exactly what we are doing today. By the end of the class, you will be able to implement all five models, use the scikit-learn package, and pre-processing the dataset for regression and classification tasks. And you will learn to evaluate model performance with metrics like accuracy and mean squared error. And then you will learn to adjust hyperparameters to improve the result. And here's the five models we will conduct today. The first one is linear regression. We will start simple predicting numbers with a straight line. And second one is logistic regression. We will tackle yes or no questions. Third one is decision trees. We will consider this a flow chart that makes decisions. And the fourth one is random forest. We will combine tens or hundreds of trees to build a smarter and more robust model. And the last one is the perfect machine. And we will create boundaries to separate complex data shapes. And this class is about practicing. So we will use the package scikit-learn, a toolkit that lets you train model in just three steps. First step is load data, and second step is model fit used to train, and the last step is model predict used to deploy the dataset. We will move fast, but I will provide all the code in a Jupyter notebook, and your job is to think and experiment. So first, let's set up our tools and load the packages we will use here. Yeah, now we have all our required libraries and packages imported and it's loaded. And next one, let's go to the second part, linear regression. In this part of class, we will learn about linear regression. That's one of the most simple and powerful tools in machine learning. You will learn how to quickly use this method to predict real-world continuous values like price, scores, or measurements. So what's the first one? What's the linear regression? Imagine that you are trying to predict something numerical, like the price of a house, based on some other value like its size. Linear regression helps you to find the best possible straight line to describe that relationship. Once you have this line, you can make accurate prediction even for new data you have never seen before. Now let's think it visually. Picture plotting your data points on a graph, and each point here might represent the size of a house on the horizontal axis and its price on the vertical axis. And then the linear regression finds the straight line closest to all those points, summarizing the overall trend. This best fit line is the heart of linear regression. And how does this algorithm know which line is the best? So here we can say it tries to minimize the error by finding a line where the predictions are as close as possible to your actual data points. Usually we measure this closeness using mean square error here like we showed, and which simply means we are aiming for the most mirror average error across all the points. Now let's look at the plot provided, and we can see here the plot. These black dots represent our real-world data observations we have collected, And the solid red line in our linear regression model, that's our predicted tool. And notice the dashed lines around our model, and this shows our confidence in predictions. Smaller intervals means a higher confidence. And lastly, you will see the small vertical arrow bars at each black dot. And these show the natural variability or uncertainty of our real data. And in our today's practice session, you will learn how to quickly implement the linear regression use Python. And you will with the scikit-learn library. And you will also see it's incredible straightforward, and you just load your data and tell Python to fit the line, and then you can immediately start making predictions. And now let's put the theory into practice and see how we can quickly build a linear regression model use Python. For next 10 minutes, I will walk you step by step through a simple coding demonstration, and feel free to follow along and run this in your own Jupyter notebook. So the first step number 1, we will generate synthetic data. Firstly, we will create some synthetic data. Essentially, fake data we generate to demonstrate how a linear regression works clearly. And we will start by setting a random seed for reproducibility. And in that way, we will get same data every time we run this code. And next, we will create our feature values x and think of x as our input variable and range from 1 to 20. And then we will generate the corresponding y values. Here, the true relationship between y and x is simple. It's y equals to 2x. But you can notice I add some random noise because we are adding a bit of noise to simulate the real world data, since the measurements are rarely perfect in the real world. And now let's visualize our data. And we can see the blue points you will see represent our synthetic observations, and the red dashed line indicates that the true relationship we used, y equals to 2x, without any noise. And then notice how the points hover around the red line, but they are not perfectly aligned. This is exactly what the real world data usually looks like. We can see here. And now let's go to the second step. With our data prepared, it's time to build our own linear regression model, right? To do this, we use a linear regression class from the scikit-learn library. And we start by initializing our model, and then we will call the .fit function. And this function will feed our data x and y. At this point, Python will calculate the best possible line to describe our data. After the training, our model will provide two key values. One is the intercept. Think of it as starting value of our prediction when x is 0, and the slope. This tells us how much our predicted y increases for every unit increase in x. Here, when we print this value out, you will clearly see how close the model got to our original equation, y equals to 2x. Remember, due to the noise we added, we will not get exactly 2, but the slope should be very close. We can see the equation we get here. Now we will go to the third step, visualizing the model performance and visualize the best fit line. To understand our model better, let's realize how our linear regression predictions compare with the true relationship. And look at this plot. Again, we plot our original data points in blue, and we include the red dashed line to remind us of the true underlying relationship y equals to 2x. Additionally, we will plot our model's prediction line in solid green and take a close look at how well the green line matches the red line and fits the data. Ideally, they should be very close and even same, demonstrating that our model effectively captured the trend in the noise data. And this spiral helps you to quickly assess if your linear regression model makes sense or if it needs more improvement. And we can see our two lines are very close. And then we will go to the last step, make predictions. Finally, let's use our training model to predict a new unseen data point. Suppose that we want to predict what our model think the value of y should be when x equals to 21 outside our original data set. And we just feed this new input x equals to 21 into our model, and Python will give us a predicted value. Notice that the prediction makes the sense give our trend is roughly double our input as expected from our original relationship y equals to 2x. And now we get the prediction. This prediction capability is precisely or accurately, and why linear regression is so useful. You can now confidently estimate the new values based on your own trained model, and in just few minutes, you have learned how to generate realistic, synthetic data, and you learn how to train a linear regression model with Python. And you also learned the virtually compare model prediction with actual data and make new predictions with your own model. And this practice workflow will form the basis of all machine learning takes us to cover this course. And then feel free to experiment afterward and changing the amount of noise or the number of points. And you can also see how the model reacts. Now let's move on and try this out yourselves. You can try to modify the noise level from the new value and rerun the code I provide you to see what happened. And now let's move on to the next model, logistic regression. In the next 15 minutes, we will learn about another powerful model called logistic regression. Even though it's also named include regression, but it's primarily used for the classification task. And it's accurately binary for the binary classification problems where outcome just have two possibilities. For example, yes or no, or pass or fail. And linear regression predicts the continuous numeric values. But classification tasks are different. They need clear categories. This is accurately, and the logistic regression comes into play. So, how does the logistic regression work? The main idea behind the logistic regression is converting continuous value into probabilities between 0 and 1. You also learned about the probabilities before, and with a sigmoid function with a characteristic S shape, as I showed here. And the result is simple. You get a probability like 0 0.8, 0 0.3, 0 0.5, 1, or even 0. And that indicate the likelihood that a given input belongs to positive category or negative. And now let's look at the provided plot here. I provide you a plot. And here each dot represents the data belongs to one or two categories, not like the linear regression in the logistic regression. For instance, pass, fail, an exam or not. And then the S-shaped curve you see here is sigmoid function that logistic regression usually use. The curve neatly ensures our predictions always stay between 0 and 1. And notice that the horizontal line at probability 0.5, this is our decision boundary. Above this line, we will predict the positive categories, and below the negative one. And now let's straight dive into the coding demonstration. And here, now let's see how to implement logistic regression using Python with famous iris dataset practically. We will use this dataset to quickly classify whether an iris flower is a Setosa species or just based on only on two simple features, the flower's sepal length and weight. And the first step number one, loading and visualize the dataset. And we will start by loading the iris dataset, building into the Python's scikit-learn library. And we will only use the first two features, sepal length and sepal weight, to keep our example straightforward and visual and easy for you to understand. We will label flowers as we put the figure here that belongs to the Setosa species as one, and all the other flowers as the class 0. And when we plot this data, the visualization clearly shows how Setosa flowers marked differently cluster distinctly from all the other species. And we can notice here from the scatter plot how the Setosa class form a separate cluster from the others. And this separation is ideally for our logistic regression model. We can clearly separate them. And we can see this figure. And let's go to next step, train a logistic regression model. Now let's train our own logistic regression model using this dataset with Python's powerful library, the scikit-learn. Train the model in extremely easy, we can see here. We simply initialize the logistic regression model and also use the feed function from the library and feeding our input data. And once the model gets trained, and the model will automatically determines the best way to separate these two classes, Setosa flower and non-Setosa flowers, based on our input features. And when we print the model parameters here, you will notice we get an intercept and coefficient. These numbers tell us how strongly each feature, sepal length and sepal weight, contribute to the classification. A larger absolute value or absolute coefficient means the feature is more important in determining class membership. Here we can observe length will take more importance than the weight. Now let's go to the next step, visualize the decision boundary. And we will visualize and the decision boundary and think of the decision boundary as an invisible line drawn by our model and that clearly separate one class from the other. Here we will plot our boundary and exiting data points. The areas shaded differently indicate the predicted classes. And ideally, you want this boundary to clearly separate your classes. And if your boundary does a good job, it means your model effectively distinguish between the setosa flower and all the other flowers based on the uh, sample measurements, weight, and height, and we can see they are perfectly separated from of purple and the yellow classes. And now let's go to the make predictions from new data. And finally, one of the best parts of logistic regression is making the predictions for new unseen data point. Let's quickly test our trained model with a new flower. Suppose that we have flower with the sample length of 5 centimeter and the width of 3.5 centimeter. And we simply feed this new data into our model, use the predict function, and the model then returns both predicted class and the probability of that prediction. And now we can see here, the probability gives us the confidence in our model and how sure the model is that the new flower belongs to Setosa or not. And here, this kind of clear probability-based prediction make this logistic regression an excellent choice for the binary class task, especially when you need interpretable result. And then in the last few minutes, we have loaded and visualized a classic dataset, and we quickly trained a logistic regression model. And we also visualize how effectively our model separate two classes. And we also make the accurate and interpretable prediction for new data with Setosa flower and 92 percentages accuracy confident. As you can see, the logistic regression in both practical and accurate give clear, interpretable prediction for classification problems. So then let's feel free to explore further by trying different features or datasets after class. And now let's just move on and try out the next machine learning model. We have learned the two basic model, linear regression model and the logistic regression model, and they are very basic model in machine learning area. That they are there for the most basic task, regression and the classification. And now let's go to the next one. We will move into another very intuitive and popular machine learning model and very widely used, the classification tree, as known as a decision tree. And because decision tree actually have the regression tree and also have the regression tree and classification tree, but classification tree are more widely used, so I will more focus on the classification tree today. So what's exactly a classification tree? Imagine that we will make a decision based on answering a series of simple questions, and each answer takes you one step close to your conclusion. That's exactly what classification tree does. It splits data into group by asking yes or no questions until it reach a final prediction. Let's look at a practical and easy to follow example to better understand this idea. Refer to this image. Here we have a simple classification tree designed to determine if a person is fit or non-fit. At the top of our tree, we can see the question is a person younger than 30? Depending on the answer, we will move to one or two new questions, yes or no. So on the left side, we ask if the younger person eats a lot of pizzas. If the answer is yes, we classify them as unfit. And if the answer is no, we will say it's fit. And on the right side, for those 30 or older, we will ask if they exercise in morning. If yes, we will say it's fit. And if no, they are unfit. And we always say we begin at the top from the root node, and then we have questions, flip the data, and for the branches, we have the branches here, L and answer until you reach an outcome. We say it's a leaf node, and the outcomes and the leaf nodes are your final classification prediction or decisions. And these intuitive branching approaches make the classification tree extremely easy to interpret because we can very clearly to see this flow. Anyone, even without technical training, can clearly see how predictions are made step by step, and you can see here very clear. And why do we like decision trees so much? First, they are very intuitive and easy to understand. It's perfect to clearly explain the predictions. And second, they handle both numeric and categorical data smoothly. And you can try after the class with different type of data set. And the last one, they allow us to really understand exactly how each decision is reached, make them great for presentations and reports. And I will show you an example later in the demonstration. And in our practical coding session today, we will load a dataset and build a tree and then visualize how it split data. And finally, see how the trees make the prediction. Now let's jump straight into our coding demonstration now. Let's go down. Okay. The step one still loading and preparing our dataset. We will start by loading the Titanic dataset directly from the website. And we will choose key features. For example, we will choose the passenger class and first class, second class, and third class, and also the gender of the passengers, male or female, and also age of the passenger. And then we will convert the gender feature into numeric form because even the decision tree can handle different data type, but for one-time training, we have to make all the type of data set consistent. And here we convert them into 0 and 1. 0 means the male and 1 means the females. And after removing the missing values, use the drop down function. Our dataset will include, you can see, yeah, our dataset will include 887 passengers from Titanic, the very famous ship, with these three features. So we have label, survived or no survived, and we have features, passenger class and gender and the age. And then let's go to the next step. Train the classification tree. So we will train a simple classification tree, and we limited our tree depth to 3 levels to keep things easy to interpret and avoid overfitting the dataset. And here's the also our code. We still use the function fit And we have decision tree classifier. We set up the depth to 3 and random state to 42, and we will train the dataset use fit function. And here's the visualization of our trained decision tree. Let's briefly examine it together. Look at this figure. Here we can see the top node start by asking about the gender, sex, or sex. And interestingly, the gender is the most important predictor here. If the passenger is male, that's coded as 0, the model moves from one pass. And if the passenger is female, coded as 1, it moves down another. So here true means 1 and false means 0. We go to the two different genders. And then we will further down the tree, and it considers the passenger class, or we say the P class here, and also the age. This additional split further refine the prediction about the survival. We can, for example, we can see when it's a female, it will consider if the age is under 13 or not. And if it's under 13, we will go to this branch, and it will ask us if the P class or the passenger class is less than 2.5. Means if the class is 1 and 2, it will go to one branch. And if the class is larger than 2.5, means the class is third class, it will go to another branch. And notice the colors in the tree. The blue nodes tend to predict the survival, and the orange node will predict non-survival. And by looking at this decision tree, we can easily understand how each prediction is made step by step. You can see it carefully. We did go to different branch, and we know if it's the passenger will be survival or not. Okay, now let's go to the next step, that evaluate model performance. So we will check how accurately our classification tree could predict the survival rate or survival or not. After splitting our dataset into train and test set, you can see here we have train and test set. So the test set equals to 0.2 means we have 80 percentages of trained dataset and 20 percentage for the test dataset. And we use this function, train test split. It will help us to split the dataset randomly to training and test set. And we also use fit to retrain the model on the train set, the 80 percentage train set, and use predict to get prediction on the test set. And then we will evaluate the accuracy. So we will compare the test result and the test set, the ground truth label, and the predicted level. After compare that, we can get our accuracy. And let's run it. Okay. So the accuracy on the test set came to 78 percentages, means our simple tree correctly predicted survival from 4 out of every 5 passengers. That's just absolutely value, and that's pretty good for such a straightforward model. And let's go to the last step, the predict for a new passenger. Finally, we will use our train model to predict survival for a fake or for our imagined new passenger here. And we can look at this value. The new passenger in the first class, and is a female, and she at the age of 25. And we will use model predict function to get our new prediction. And also use the predict proba to get our probability of confidence. And when we input this passenger's information into our model, the prediction is very clear. The predict class is survival, and the probability of survival is 98 percentages. And that's the classification tree. They will offer us both predictive capability and clear interpretability. We can get the prediction and also the probability of getting that prediction. And actually, I really encourage you to experiment with other datasets or just change the parameters like depth of our tree by change the max depth to see how it affects your result. Yeah, that's it for the classification tree, and we will now move forward and explore our next machine learning model. We will move on to our next powerful machine learning model, random forest. Think of these as an upgrade from a single decision tree. So random forests are from decision trees, and because it's a forest, so there's a lot of trees we will consider at the same time. So random forests are among the most popular machine learning method today because they are simple yet remarkably effective at handling complex dataset. So what's exactly the random forest? So imagine that you are trying to make a crucial decision. Would you rather rely on just one expert's opinion or just ask several different experts and then combine their advice? So you might understand the random forest works exactly like this. It uses a forest of many decision trees to reach a final decision. So here's how it works step by step. So instead of building just one decision tree, the model will construct many different trees with same dataset. And then each of these trees is trained on a slightly different set of data and a randomly selected subset of features. And for each new prediction, every tree gives its opinion independently. Then the random forest that will combine all these predictions to get a final decision. So when it's classification task, it will take a majority vote from all the trees. And for the regression problem, it will average out of all these predictions from every tree. So just like this figure shows, we have our data set and we will have slightly different subset to train the different models, different decision trees. So in that case, they are just slightly different, and the tree will get kind of slightly different information and have their own training process. And after that, when we want to get a final prediction, they will have different results, and we will do the voting or averaging to get a final result. So why does it works well? So by using multiple trees, random forest can significantly reduce the risk of overfitting. Even if some trees make mistakes, their errors tend to cancel each other out when we aggregate many trees and making all the overall prediction very accurate and stable. So look at the illustration. Also, we get back to the illustration we provide. You will see multiple individual trees, and each of them independently make decisions, and then their prediction are combined to create one very robust and reliable result. And then we will go into our coding demo and see the random forest in action. So we will continue to explore this random forest using the Titanic dataset. And we will use the same three features we used previously in the decision tree: passenger class, gender, and age. And so here we will directly start from the train the random forest model. So we trained our random forest model by using 100 individual trees. You can see number of estimate 100 individual decision trees, and each tree will be built from slightly different random subset of the data and features, which helps ensure our model is robust and less to the overfitting. And finally, we will test our model prediction capability on a fake passenger. So we will firstly train the model, and we can see the accuracy on test set as I described before. We have training set and testing set, and the accuracy on the test set is 0.76, means 76% accuracy. And to and we will also have the feature importance. It's specialized for the random forest. It will tell us which feature will be more important, and we can see the age is the most important feature, and then it's sex, and then it's the passenger classes. And if we imagine that there's a passenger who's 25 years old and a female, and in the passenger class is second class, and our model will predict that the passenger would mostly survive, and we will have a very high confidence. The confidence will be actually 99%, and according to our random forest model. So you can feel free to experiment, do some exercise after class by adjusting the number of trees or including additional features, and see how your prediction will be changed. And now we will go to move forward to our final model for today. The last model we will involve today is support vector machine. We also said it, or we usually said it as SVM. So we will go into our final machine learning model for today, support vector machine. And SVMs are among the most powerful and widely used classification method in machine learning. Even it's just proposed in last century, 90 something, but it's still very widely used and very popular in some really recent research because it's really strong and powerful. So how does support vector machine work? So now let's imagine that we have two groups of data points and you want to clearly separate them. And support vector machine did this by finding the best possible boundary, or the technical terms we called it a hyperplane that divides this group with the wide margin. So this margin is a gap between the boundaries. You can see here between the boundaries and the nearest point from each class called the support vectors. We can, support vectors here, but we will not go very deep of that today. So now sometimes our data isn't easily separated by a straight line, because we can see in this figure, because for your better understanding, I show some figure example, but in the real world data set, there rarely a problem can be separated by so simple line here. So perhaps it's mixed together or follows very complex patterns. In such class, SVMs use something called kernels to cleverly transform data into higher dimensions. make it possible to separate classes effectively even in the tricky situations. And take a quick look at this visual example I provide here. So the solid line is the best boundary founded by support vector machine. We have two classes, the blue class and green class. The boundary help us to separate them clearly. And here the dashed lines marks the margins, which the support vector machine tries to make as wide as possible, because there's possibly some samples very close to the boundary. So in that case, if we have a wide margin, it will help us to have a more stable prediction and classification result. You notice those special points here on the margins. So we call it support vectors right at the edge. They will determine exactly where the boundary is placed. And then let's go to the coding demonstration now and experience how support vector machines tackle the classification problems. Here, yeah. Now we will see support vector machine in action. We will apply support vector machines to a classic synthetic dataset called Moon's dataset, which beautifully illustrate here how a support vector machine can handle the complex and nonlinear patterns in data. So first, let's understand our dataset. We will generate the Moon's dataset with two, you can see, the interleaving and half moon shapes, as you can see clearly from this plot. So the points here are colored differently according to their class. One moon is blue and the other moon is red. And notice how the classes are not linearly separatable by a simple straight line. This makes it perfect for demonstrating support vector machine capabilities. You can see here the two moons. And let's go to the next step. Train and support vector machine and evaluate. So next we will train our support vector machine model using a kernel called RBF, radio basis function. And in that case, this kernel is ideal for capturing the complex and nonlinear boundary required for the dataset like this, like the moon dataset. And after training, we will evaluate how accurately our model predict the correct classes on the new data. And our supplemental machine achieved accuracy of 97% on the test set. And this means it successfully distinguished the two classes correctly in nearly every cases, because 97% is pretty high in machine learning area. That clearly shows the power of support vector machine for nonlinear problems. And then we will go to the third part, visualize decision boundary, because we also want to see how it works in our eye. So let's now look at the support vector machine's decision boundary visually. Okay. So the plot here shows the decision boundary. We can see very clear. There's shadowed blue area and shadowed red area. And this is where we see its power clearly illustrated. So in this form, to distinct the blue and red regions, each represent the predicted classes. And we can notice how smoothly and cleverly the support vector machine boundary curves around the two moon-shaped clusters of points. And clearly, the model finds a highly effective and accurate way to separate these two classes. And in our last part, we will make a prediction on new data point. So finally, we test our model on a completely new data point with the coordinate 1, 10. It should be here. 10 will be here. And our model confidently predict this point belongs to class 1, which is red point in our plots. And this result make perfect sense because visually align with the region identified by our model in the decision boundary plot. Here, it should be here. So also for this support vector machine, I also highly encourage you to experiment after this class with different kernels and parameters to see how support vector machine performance can be. And with that, I will ramp up to all the code later and help you to understand more about my code. We have introduced the concept of all of the models, and now we will go through the code line by line so you will understand exactly what's happening under the hood and how to tweak if you for your own project. So we will go to the first part, the importing the libraries. So here we have several libraries. Let's starting by importing the necessary libraries. So here the NumPy is used for the numerical operations, especially with the arrays and the metrics in Python. And also the pandas is great for handling structured data like tables or spreadsheet. So I'm not pretty sure if you known Python before or not. So usually we import NumPy as NP, pandas as PD because for the convenience when we use it in the following coding work. And we also import the matplotlib dot pyplot. So it's our plotting tool. It's very important and will let us visualize our data and our model. And then we will have the train test split from sklearn model selection. That will help us to split data into training and testing set later. Through we have our whole data set and for the machine learning training, especially for machine learning training, we will always split data to training data set and testing set. And you have to remember that in the following learning and following programming to split them. And next, we also import the S from the sklearn to import several packages, including the linear model for the linear regression package and logistic regression package. And in the sklearn, we also have decision tree classifier, plot tree. So the import linear regression model from the sklearn. So it's a widely used machine learning library in Python, and this specific class lets us to feed a straight line into our data. And also for next, we will have our decision tree, and we will plot the tree as the figure I showed you. I use this package, and also random forest, subvector machine, SVC. They're all packages from sklearn. So that's very powerful package we will always use in the machine, especially for the basic machine learning model training. And then let's go to the data generation. So for generating our data set, we create the data set with several lines of Python code. So np.random.seed that ensures that every time we run this notebook, we will get the same random numbers. This help us to make our result reproducible. Especially for example, it's very important to let it to be repeatable. So you can also remember this function random.seed. And for next one, x equals to np dot arrange and reshape. So that means we generate a sequence from 1 to 20. Range of 1 to 20 is that's from 1 to 12, but the range actually is 20. And these are our input values or features. And we use reshape 0, 1 to 1 to turn it into a column vector because sklearn expects the features in a 2D format, even if it's just one column. And for y, we have function here. We define a linear relationship. Y equals to 2x plus noise, and x dot rival flattens the array, so it's 1D list of numbers. You must focus on the data type, list, array, and some vector when you code by yourself. And also the np.random.ran times 2. That's help us to add random noise to simulate real world data. Our line isn't perfect because, as I said before, and to plot the raw data, we have this group of code, and you can usually use this kind of code to plot your data set. And so you can remain or you can copy and paste to use this group of code. So here the plot dot scatter. So that's the scatter is a very specified function in the plot. So it can plot the noisy data points in blue. So plot will plot the line, but the scatter will plot in the dot. It's pretty similar in the MATLAB. And we also plot x and 2 times x to draw the true underlying line without noise in red dashed style. This represents the ideal relationship y equals to 2x and color line style and have label here. And we also have the label, legend, and title, and you might also understand many of them: label X, label Y, title, and legend on the left top kernel. So then you can see our plot with blue dot and red dashed line. And then we will go to the training model part. We train the model using the function linear regression. It's very simple to initialize the model. Using model equals linear regression, and then we use model.feed. It's very important function. We will use it for most simple machine learning models. It's help the model learns the best fit line by finding the optimal values for the slope and the intercept that minimize the mean square error between the predictions and the actual value y. And then we get the train model. We have the function here. We print the function here. Here the beta 0 and beta 1 equals to the intercept and the slope. And now we will go to the, we can load the intercept and the slope as a coefficient. And we will go to the visualize the best fit part because that's also important for you in the future when you do some research project or you do your class project homework. You want to visualize the fitted line and the ideal line. So it's a very helpful plot. It can compare the three things: the original noisy data points in blue dot, and the true line we use to generate the data in the red dashed line, and the model predict line in green. So it's also pretty similar to the previous plot you can look at in the after class and try by yourself. And then we will go to the next step. Go to this part. So we use our train model. We have model, train model here. So we have used this model to predict the new value of y with the new value of x equals to 21. We will wrap 21 in double brackets because the model expect a 2D input in shape, one row, one feature. So that's for the data type in the linear regression. And then the model used the formula y equals to beta 0 plus beta 1 times x to compute and return the prediction we can see here. Use the predict and we can try change the value from 21 to 30 and or any other number, and we can run it. Sorry. Yeah. So for x, we will have a new y 55.77. So you can also try after this class. So after finishing the linear regression code, we will go to our logistic regression. And as I said, even it's also called regression, but we still use it for the binary classification in our code. So we'll go through the code still step by step to understand what each part does to classify our case, the setosa flower or no setosa flower. So firstly, we will load and prepare the arrays dataset. So we will from the SQL to load this dataset. Can see the arrays equals to load arrays. If you run it, yeah. So it's a typical or classic dataset from the skiller for us to do the binary classification examples. Then we have the X arrays and Y arrays here. So firstly, you know the arrays dataset is built right into the skiller, contains 1 and 50 flower samples across 3 species: Setosa, versicolor, and Virginica. And each flower has 4 variants: sepal length, sepal weight, petal length, and petal weight. So we only use the first feature, as I said in the comment also. The first feature is sepal length and sepal weight for easy 2D visualization. And then we will create a binary classification target. So the arrays target equals to 0, identify the samples and that are setosa. And here the S type int converts the true false the boolean to the 1 0 to the int. And now we will try to answer is the flower sesota or not. Yeah, here's our plot. So just as I introduced in the last part, we will have the scatter for x and y. And here we will also have the label title, and we have a color bar to show the color, the 0, 1 to different type of the flowers. And that indicate to 0 is not sesota, so it's just blue, 1 is sesota, just yellow, that help us to clearly see which class is it. And then we will go to the next part. train the logistic regression model. So it's still from the I recall this import from the skler. We import the logistic regression package. So still we use model equals to logistic regression to create and initialize the model and use this function fit to train it using our features and our binary labels because we have X arrays and Y arrays from the last step have features and labels to train the model. And behind this sense, it's using a sigmoid function as I introduced. And you can also search on internet to learn more about the sigmoid function because sigmoid function is really widely used in machine learning training, not only in the logistic regression, even sometimes in the convolutional neural networks to map the predictions into the probability between 0 and 1. And it then will find the best coefficient that separate the classes as clearly as possible. And then we will get the intercept using the model intercept function. And the intercept is a bias term, also beta 0. And the coefficient we got from here, the coefficient represent the weight for each feature. A positive coefficient push the prediction toward to 1, also as known as a Setota flower, and a negative coefficient will push it towards 0, not Setota flower. So these values are useful for us to understanding which feature are most influential in the classification, just like shows here. And we will go to the next step. Yeah, the next step. So we realize the decision boundary. This part help us to create a grid of X and Y values to help us plot the model decision. So this function, NP mesh grid, creates a dense grid of points across our feature space. And then we will use the predict function to predict the classes of each grid point. And here Z is the predicted classes at each location in the grid. So then we will still use a group of plot to plot the decision surface. This gives us this visual map. Light and dark areas shows where the model predict Satora versus not Satora. And you will see a small line, the small line here to divide the two zones. That's the decision boundary. And also, this shows exactly how the model would classify any new data points based on where it hands on the plot. Now you can feel free to change any hyperparameters here to see what happens by your own. That will give you a more impression experience of the code here. And then we will go to the next part, prediction. And yeah, so we will test the model. We create a new flower with the sample length of 5 and the sample weight of 3.5. And here the predict proba gives us the probability of each class and also the predict function. Still, we are kind of familiar to it, right? And it gives us the final class of prediction, 0 or 1. In this case, you will likely to get a high probability of Satora because this point falls within the decision area of class 1. So you can play around with the different value here and see how the model react. And you can try to change the weight or length and rerun the block here. Maybe you can try 7.5 and run the code and it's still Satora and the probability get higher. And you change this to 1, you can play with it, it's Satora, and maybe 10, it will be not Satora. So probability of zeta ray is 14 percentages. And that's for the logistic regression. And after this class, you can play with this code and try by yourself. We'll still go to the classification tree. So remember that we have built a model that predicts whether a passenger survived or not in the Titanic disaster based on just three features: passenger class, sex, and age. So let's go through the code together step by step. So here the model the data we still load from outside from internet here. We are pulling the Titanic dataset from the public URL using the pandas. So Pandas is also a powerful package. We usually use it to deal with data or load data. It's pretty powerful, and if you doing some research or doing your homework with machine learning, you cannot avoid this package. You have to know the knowledge of it. So it's our go-to tool for handling tables and a spreadsheet. And here the dataset includes the passenger's information such as name, age, ticket class, sex, and whether they survived. And we will print the column names just to confirm that we have working on it, we have survived or not. And passenger classes, name, sex, age, and something else, but we didn't use in our case. And also we have shape. It means we have totally 887% passengers and three features. We can extract sex and map them to, as I did before, 0 and 1. And we extracted these features from the totally datasheet and drop the missing values, and we have the survived ones. And then we will go to the data pre-processing. So that's also a very important step in machine learning. So just as I showed you, the Titanic survived passenger classes, sex, and range. We keep only relative columns, survived P class, sex, and age. Convert age to column to numbers, 0 for male, 1 for female, because machine learning models works best with numeric input. So always transfer the text to numbers. And then we drop any rows that have missing values, use this function. It's also important in your own study. And this is a quick fix, but in real world project, we might try to fill in the missing values instead, but that's a bunch of work, so we will not introduce here today. And then we split data X and Y. X contains all the features. We'll just we drop the survived column, and for the Y, we our target. So whether passenger survive or not, we just pick up the survived column. So now we have a clean data set ready to go. And then we will go to the next part, train and decision tree. So from sklearn, I just recall them lines here. So I recall it to highlight the packages we use in this part, the decision tree classifier, plot tree, and plot. So let's train our decision tree. We will import, after we import these three packages, we set up the decision tree classifier. We have the max steps equals to 3, limits the tree to 3 levels deep, and that keeps the things simple and avoid overfitting. And also we have the random status state into the 42 that ensures we get the same tree every time when we run the code. So if you also want to keep the same same tree, you can also make this hyperparameter as 42 to keep it always same. And then we use the feed function to train the model on our full data set with our X titanic and Y titanic setup from last step. So then we will visualize our decision tree. So that's the most powerful part in the decision tree. So you can visualize it from the logic. So plot tree, this function will help us to create a beautiful flowchart just as shown here. So each node shows the rule like the sex less than 0.5 Gini impurity. That's a mirror of how mixed classes are and how many samples pass through the node. We have the value that shows how many samples are passed. And also we have the class prediction at the point. And you can literally read this tree top to down and ask yes or no questions, just like a human would. Like, is the passenger a female? If yes, we will go to next step and ask, are they in the first class? Just as so on. And we will go to the next step, the train, test, split, and evaluation after we realize the decision tree. So here's the two main package we use in this part, the train test split and accuracy score. So we want to evaluate how well our tree performs to unseen data. So we split the data set from to the 80 percentages for training and 20 percentages for testing by set up this hyperparameter. And we retrain the model on the training set here in this code, use fit, X train, and Y train. And then we will make predictions on the testing set using predict function. And we have the test set of feature test, and we have ground truths of labels. And finally, we will compute the accuracy, use this function accuracy score to compare the predicted labels and the test labels to calculate the accuracy. And you should see something like 78 percentages accuracy, which is great for a simple model trained on only 3 features. And the last step is to predict a new passenger. So as we did before. So in first class and female set as 1 and 25 years old. And still use this function model.predict to give us a class label 0 or 1. And we also use the function of predict of probability that gives us a probability or the confidence of each class. So we can see how confident the model is. Here the model says the passenger survived with around 98 probability, depends on the training. And you can easily change these input values. And you can try making the passenger male, older, or in third class. That can be observed how the prediction changes. For example, you can change it to a mile, and it will be now survived. So you can freely change by yourself after this class to see what happened. After the decision tree, we will still go to the random forest. So far, we have worked on individual models, logistic regression, and single decision tree for the classification task. And now we will have our embedded trees, the random forest, for the next step. So the many trees, many weak learners, and work together to build a strong learner, the random forest. And this usually lead to a better accuracy and more stable results than a single tree, but sometimes it not very absolutely. So sometimes for very simple problems, decision tree can be better, but not always. So we will start, and as I said before, we will still use the Titanic dataset for our random forest training. So we will skip the data loading part and directly go to the train the random forest model. So first of all, here's our necessary package or libraries for the random forest training. So the random forest classifier is the class we will use to build our random forest. And still train test split will help us divide our data into training and test sample or test sets. That's pretty important for the machine learning training, and you have to remember that and use it into your own study. And also on class accuracy score help us to mirror how well our model is performing. Then we will go to the split dataset. Still, we have X and Y, and we split the test and training set. 80 percentages for training, 20 percentages for testing uses hyperparameter. And still random state equals to 42 ensures our repeatedly, and we will have the same split every time you run it. So far, the setup is same as what we use for the decision tree. It keeps our comparison file. And then we will go to initializing and training the random forest. So here, random forest classifier, and we use it for create and initialize our model. And here, the two hyperparameters n estimators equals to 100 means we will build 100 trees. And you can freely, after the class, you can freely increase or decrease this number to improve the performance. But sometimes for the more trees will take a longer time for training, but our example is simple, so you can freely change the number here. And still random status equals to 42. Again, help us to reproduce constant result. And then we will use the fit function to train the model just like before we did multiple times, and you might have remembered it. And one great feature of random forest here is that it's automatically handle overfitting better than the single tree, because we have randomness in tree creation. And then we will make the prediction and evaluate. So we still get prediction from the prediction function and with the test set of features. And then we use the accuracy score function to compare the tested labels and predicted labels, and to calculate how many samples are correctly predicted. And then we get the accuracy 76 percentages. So still remember these two functions. Predict give us the predicted classes for a test set, and function of accuracy score compares those predictions to the true labels. So we will go to the next step, the visualize feature importance. So we recall this package plot. And random forest has a built-in feature that tell us which input were most important for making decisions. Because feature importance or feature selection is a very important topic in machine learning nowadays. Because we besides to get prediction, very accurate prediction, we also want to know deeper about how the model makes this kind of decision. So we want to find which factor or which feature are really important. So we want to select the important one to explain more to the audience or the readers. So here we have the RF model dot feature importance that gives us a numeric score of each input feature. And in our case, we have P class, sex, and age. So when after we run this code, we get a bar chart here, shows which features our model rely on most when predicting survival. For example, the age is most important. So the younger passenger might more likely to survive. That helps us to interpret our model and build trust in the prediction in the future. And then we will go to the next step. Yeah, here the bars will help us to plot the bar plot as I showed here. You can also use this function to plot a lot of bars for your own study. Next step is to make prediction. So we test our model on a new passenger, P class equals to 2, and the sex is still female, and age is 25. And still use the predict function that gives us the predicted class. 0 is didn't survive, 1 is survive, and predict probability function that gives us the model confidence or the probability that passenger would survive. In this case, these two functions are very important also for your study. And you will likely see the models predicted and probability, and that also helps us to explain to anyone else how we make this decision. And we can also try to change the values just as I did in the decision tree part. Set the passenger to mile or change class to 3 and see how that affects the output. That's a very great way to explore how the model thinks. So let's go to the next part, support vector machine. Our last model of this class. We have worked with linear models and tree-based models, but support vector machine is particularly good for those non-linear separable data set. In other words, this kind of data cannot be cleanly split with a straight line. So this is where SVM really works. So we will go to the code and explore how it works. So let's start with the data generation. We are using a building function called makeMoons to show our moon dataset to generate a 2D dataset, 2-dimension, feature 1 and feature 2, with a nice curved shape. So it creates two interleaving half-moon shapes. This kind of data is not linearly separable, which is exactly why we are using it to test support vector machine. And we generate 200 points, number of samples 200, and with a little bit of noise equals to 0.2 to make the problem more realistic. But still, you must be very familiar to this hyperparameter to make this more repeatable. And you can adjust the noise level. Lower noise, more separable, or harder or higher noise will be a harder problem. And then we will visualize the dataset. We still have this group of functions and use a scatter plot to see the data. Each point is colored by class, and visually it's obvious a straight line will not work here. And this is good for testing support vector machines function. And then we will go to the data splitting. Still, we use SVC. We recall all these packages to show which packages are necessary for this part. SVC still these two, our old guy, the train test split and accuracy score.
in this time, because we have 200 samples, so we have a different ratio of train and test. 70% is for training set and 30% is for test set. Still make this model or this code more repeatable for our experiment. And now we will be ready for training this model. So next step is train the support vector machine model. Here we have because we have SVC function. So these two lines are the heart of this demonstration. We create and train the support vector machine model using SVC function, which stands for support vector classifier. And we will break down the key parameters. The kernel equals to RBF. This is radio basis function, as known as Gaussian kernel. You might familiar with Gaussian. It's used to handle nonlinear data like this. And here we have C equals to 1.0. This controls the trade-off between maximizing the margin and minimize the classification error. A smaller C means a larger margin, but possibly more misclassified samples. And a larger C focus on few errors but could overfit. So here we just choose a default value of 1. And also the other parameter gamma, so that control how far the influence of a single point reaches. So the scale is the default value that calculated automatically from the data. And you can also do experiment. You can search this function on internet and find out all the possible value of the parameters. Because the scale is a default, you can choose like gamma equals to 1 or gamma equals to 0.1 to see the different decision boundaries. Here we just simply show you an example with the default value. And then we feed the model with our training data, use feed function. Also, you might be very familiar with this class, with this function feed with X-train and Y-train. And then we will evaluate this model. So we still use the predict function and accuracy score function to predict the classes for the test set. And then we compare the predictions to the ground truth using the accuracy score. And we get the 97% of accuracy. Depends on the noise and random state. It's really good. And then we will go to the next step, the visualize the decision boundary. So we can see here the code still create a grid of points. So we can visualize the model decision surface. The mesh grid function create 2D, two-dimensional grid of coordinates. And here np.c that stacks the grid points together into a list of input. Then we predict the class for each point and reshape it into a grid of plotting. And then we will still use this group of functions to highlight our result. So you will see here the colored regions showing the model classified spaces and the decision boundary. It's not a straight line, but a curve. It's smooth and curved shape that were around the moon patterns. And now we go to the last part of this code and last part of this class, make a decision or make a prediction. So we test the model with a new point coordinates 1 and 1, 0, and use this function predict to return the predicted value or class 0 or 1. Based on the location in the plot, we can barely check it if the model make a reasonable decision or not. We can also easily change the coordinates here, maybe 2 and 2, and we can run the code and try to see, okay, it's in the class 1 and check if it's correct. and you can do that experiments after the class. And I will also introduce more complicated models in the next class, such as CNN, LSTM, and transformers. Thank you for your listening.